Okay, back to the problems that we set up before the end of the last video. We've got a radio-controlled car moving around on the floor, which is pictured here on the plane of the page. And we're imagining at some time t1, its velocity vector looks like this. At time t2, it's actually turned somewhat down and to the right, and it's got a different velocity vector, which has about the same length, but different direction. Draw and label delta v. So how do we do that? Well, one way to do it is to put the vectors with their tails at the same location. We can always move an arrow that represents a vector to any other location without changing its magnitude and direction because those arrows both represent the same velocity vector. And then once we've done that, to draw delta v, we go from the initial tip to the final tip. So delta v looks like that in that case. That's not too interesting. It's a little bit more confusing in this case. Oftentimes, students see these two vectors, which are supposed to have equal lengths, opposite directions, and they say, delta v is 0. It's not 0. The sum of these two vectors is 0, but the difference in the two vectors, or the change in the two vectors, which is delta v, if you have two vectors that are pointing in exactly the same direction with the same length, then the difference in those two vectors is 0. If you have two vectors that are pointing in opposite directions, there's been a big change in going from one vector to the other vector. So delta v, well, what do? We do the same construction. Put the second vector with its tail at the same location of the first, and then we draw from the initial to the final tips. Since I didn't want to draw them right on top of those vectors, I drew them just adjacent to it. So the vector delta v is actually twice as long as either one of those and points in that downward and to the left direction. Remember this example, because when we discuss momentum later on, that will be important for us. For right now, I think I have a few voting questions and conceptual questions. So first, a rocket shoots straight up from the surface of the Earth. Is its velocity vector positive or negative? The answers are positive, negative, not enough information, or the question makes no sense. All right, when we have voted on this in class before, I always get a variety of answers, and people are very sure they know what's going on. The real answer in this case is that the question makes no sense. So oftentimes people will vote for positive because they'll think, well, plus y always points up. Well, plus y doesn't have to point up. So it's not necessarily positive. But furthermore, even if you take plus y going up, that doesn't mean that the vector itself is positive. What that would mean is that the y component of the velocity vector is positive. So, the velocity vector might be shooting up from Earth, and maybe I take my x-axis pointing 45 degrees upward from the surface of the Earth. My y-axis is pointing 45 degrees downward from the surface of the Earth. In that case, the x component of the velocity vector would be positive, the y component would be negative. What do I choose then? If somebody asks me about the sign of the vector, vectors don't have a sign. Their components have signs, but the vectors don't have signs. So it's not that there's not enough information given. Even if we knew the x-y axes, that wouldn't tell us what the sign of the velocity vector itself is. Velocity vectors, or any vectors, don't have signs to them. They have a magnitude and a direction. They're never positive or negative. So the question makes no sense. Their components can be positive or negative as long as you know what the coordinate system is. But the vector itself is never positive or negative. It's a little bit of a trick question. I don't have too many of these voting questions that are tricks like that, but very few people choose D when we vote on it. Second one, for motion in two dimension, is it possible for an object to change its velocity without changing its speed? Yes or no? The answer is yes, since when we say velocity, velocity is a vector. And there are two ways that you can change a vector. You can either change its length or you can change its direction, or of course you could change both at the same time. But if you change anything at all about a vector, you've changed the vector. So we can change its velocity vector by just merely changing the direction. If you keep the length the same, the speed is the same, but the velocity, which is a vector, has changed. So the answer is yes there. For motion in 2D, is it possible for the velocity of an object to change without ever changing its acceleration? Yes or no? The answer here, again, is yes, and it's a matter of disentangling a sentence that sounds superficially confusing but isn't saying anything mind-blowing at all. Usually when you have constant acceleration, that means that the velocity is changing, right? So is it possible to change the velocity without changing the acceleration? I imagine I'm accelerating north constantly. Usually that means I'm changing my velocity. So yes, it's possible, right? I start at rest and then I head north faster and faster. My velocity is changing, but my acceleration could be constant. So it only sounds superficially contradictory. This one's not really a voting question, but it's something just for discussion, so I'll try to do the discussion here solo, although we usually do it together. Plane is flying horizontally, shown in the picture. Call the direction the plane is flying plus x and upward plus y, so I've shown those axes down in the corner here. And we are going to take air resistance into account in what follows, because a skydiver is going to step out of the plane without jumping significantly. Now this plane is going really fast, and if you step out of the door of a plane, you're going to feel a huge blast of wind in the face, even if you don't jump at all. If you just as gently as you can, just step off the edge of the plane, you're going to be blasted by the wind going by you. So, at the instant she is airborne, in which direction is her velocity relative to the ground, and in roughly which direction is her acceleration? Acceleration is the direction in which her velocity is changing. Okay, so as she steps out of the plane, well, all of a sudden the plane was holding her up and keeping her from falling. So she certainly is going to start falling. Well, let's talk about her velocity first. As she steps out of the plane, she doesn't try to jump at all. At the instant she loses contact with the plane, she's still moving along with the plane. And so her velocity vector is going to be in the same direction as the velocity vector of the plane, which is in the plus x direction in this particular case. So right after she just slowly pulls her leg away from the plane, she is going to be still for an instant moving along with the plane. Now that's going to change. She will slow down because the wind is going to slow her down, but also gravity is going to start pulling her down. Okay, so but at the instant she's airborne, she's still moving essentially along with the plane. She hasn't had time to change her velocity much yet. In which direction is her acceleration? Well, it certainly is true that she is going to start accelerating downward, right? She's going to start falling towards the Earth. So this velocity vector is going to start tipping downward. But it's also true that it's going to start getting shorter in the horizontal direction, because she may be going hundreds of miles an hour, and very quickly that wind in her face is going to slow her down compared to the plane. So the change in the velocity vector is going to be somewhat back to slow her down and somewhat down to speed her up in that time period. So the acceleration vector, just very qualitatively, would be somewhere between downward and backwards direction. The backward part from the wind resistance, the downward part from the acceleration due to gravity. Question 2. So she's been falling for quite a while, but not long enough to hit the ground. She is essentially falling straight downward, and she hasn't opened her chute yet. So a lot of times skydivers jump out of the plane really high up, and then they fall for a while and just play around in the wind and sort of coast around. So she's been falling for a while. She's falling straight downward at this point. That she has slowed down and is not moving horizontally relative to the ground, but she is moving vertically. So she pulls her parachute cord. There's a very brief time after the parachute just pops open that she feels a strong tug on her shoulders from it, right? You open that parachute, you feel a big tug, right? It's got to, change your velocity. During that period where she's feeling the strong tug, in which direction is her velocity relative to ground, and in which direction is her acceleration? When I've asked this in class, usually there is a student or two who will say her velocity is upward during it after she's just pulled the chute and she's feeling that strong tug. She feels an upward tug, on her shoulder. She's being pulled up by the chute, and therefore her velocity's got to be upward. But we know that's not true. When you watch someone falling from the sky, they don't actually start shooting upward from the ground like a rocket. They've been going really fast towards the ground, and they only slow in their progression towards the ground. So her velocity relative to the ground is still downward, even though you might trick yourself into thinking it's upward. You know it's not upward. You don't see skydivers shooting up from the earth when they pull their chute. They only slow down in their progression towards earth. In which direction is the acceleration? Well, a moment earlier she had a huge velocity vector downward. Now she's got kind of a moderate velocity vector downward, so the change is in the upward direction. We could even use our reasoning from our one-dimensional motion stuff, because she's really moving in one dimension in this part too. So her acceleration is upward. She's changing from a big vector downward to a smaller vector downward. The change, if you go from the tip to the tip, if you put the tails at the same location, would be in the upward direction. 3. What was the magnitude of her acceleration just before opening her chute? I'm trying to phrase it in such a way that it sounds like she's reached terminal velocity. So if she's reached terminal velocity, that means she's falling downward at a constant speed. That means her velocity is not changing. If her velocity is not changing, her acceleration is approximately 0. It may not be exactly 0, but it's going to be very close compared to her acceleration at other times in the falls. And let's stop the video there, and we'll work a little bit more with our generalization of the kinematics equations after we come back.